An object at rest remains at rest, and an object in motion remains in motion. Apply a force, and that force equals mass times acceleration. That elegant math contains a strict condition. The equation F equals ma only yields correct answers if you are measuring from inside an inertial reference frame. An inertial frame is a coordinate system that is either at absolute rest or moving at a constant velocity in a straight line. If your own environment is accelerating or turning, the baseline rules of classical mechanics fail to predict what you will actually see. We live on the surface of a spinning sphere. Because the Earth rotates around a central axis, indicated by this vertical angular velocity vector, every point on its surface is continuously accelerating. The Earth is a non-inertial reference frame. When they attach a local coordinate system to the spinning ground, straight paths warp. To accurately track motion on Earth, we cannot abandon Newton. We must adapt his equation by calculating exactly how a rotating coordinate basis generates what physicists call fictitious forces. This figure illustrates the simplest non-inertial scenario. We have a stationary frame, O, and a second frame, O', that is accelerating linearly away from it. The relationship between the two is basic vector addition. The position of a particle in the stationary frame, vector r, is equal to its position in the moving frame, r', plus the displacement of the moving frame itself, vector r. Take the second time derivative of that position equation. This gives us the relationship between the accelerations in both frames. The acceleration of the object in O equals its acceleration in O', plus the acceleration of the frame O' itself. If we rearrange this to solve for mass times acceleration in the moving frame, ma', we get the true physical forces minus mass times the frame's acceleration, a. That extra term, negative ma, is exactly what we define as a fictitious force. A fictitious force is not magic. It is strictly the mass of the object multiplied by the acceleration of your measuring frame, subtracted from the physical forces at play. Now we upgrade the problem from linear acceleration to rotation. Imagine frame O' rotating with an angular velocity relative to our stationary O. These diagrams track a single particle over a tiny time interval, delta t. During this interval, the x' and y' axes of the rotating frame have turned by an angle delta theta. The particle's displacement measured in the rotating frame is not equal to its displacement in the stationary frame. This discrepancy exists entirely because the axes doing the measuring have changed direction. Here in figure 31.9b, we isolate the geometric difference between those two displacement vectors. The magnitude of this difference vector is bounded by the arc length created by the rotation angle. Apply the calculus limit. As the time interval delta t approaches 0, this difference vector becomes perfectly perpendicular to both the axis of rotation and the position vector. In linear algebra, that perpendicular geometry is the exact definition of a cross product. This yields our velocity transformation law. Velocity in the stationary frame equals velocity in the rotating frame plus omega cross r. The cross product is born strictly from the geometry of rotating axes. The stationary velocity is the rotating velocity plus the tangential velocity of the frame itself. This velocity equation reveals a universal transformation operator. It dictates how to take the time derivative of any vector translating between a stationary and rotating frame. To find acceleration, we feed our newly derived velocity vector back into this universal operator. We expand the first half of the operation, taking the derivative of the velocity vector with respect to the rotating frame. Then we expand the second half, the cross product of the angular velocity with that same velocity vector. Combining these terms produces the complete acceleration transformation equation. By taking the derivative twice across a rotating boundary, two new highly complex kinematic corrections emerge directly from the math. We bring this derived acceleration equation back to our starting point, Newton's second law. This animation tracks a mass moving inward on a rotating platform. We substitute our expanded acceleration terms into F equals ma' and isolate the fictitious forces on one side of the equation. The first isolated term is the centrifugal force. It points radially outward and depends entirely on the object's position vector, r. The second isolated term is the Coriolis force. It acts perpendicularly to the object's direction of motion. Notice a critical distinction here. The mathematical existence of the Coriolis force depends entirely on the object having a velocity, v prime, relative to the rotating platform. If the object sits still, the Coriolis force is exactly zero. Centrifugal and Coriolis forces are not physical pushes applied by interacting bodies. They are geometric corrections required to make linear mathematics work in curved spaces. Whenever you observe weather patterns, launch a rocket, or run a physics experiment on Earth, you are sitting inside frame O prime. Calling these forces fictitious does not mean they are illusions. They dictate physical reality in a rotating environment. The cross product provides the exact mathematical bridge between what an inertial observer sees from the outside and what a rotating observer experiences on the inside. Newton's laws are sound, but the universe rarely provides us with an inertial place to stand. Mathematics is the tool we use to close that gap.